Alright, here we are in my much messier living room. Just wanted to show what I've got so far. So right now I'm wearing my APCO first free flight harness. They recommend this for people who've never free flighted before, and that's me. But very simple harness. One across the stomach, one on each leg, and that's that. I'm doing this because I need to know how big my battery is. Using these little modular connections that it's got, I can rearrange the pack a few ways, but what I'm actually going to be doing, I think, is this setup, which is, oh, that's reflective. It's a 8x9, so just barely slightly long on one side. I'll go over why just in a bit, but that is right where it's going to sit. The rod will push right here. It's hard to show on one hand. Just behind this strap is where the tube will go, and the tube will be pushing on the riser, and the battery will be suspended from the tube. So this makes good use of the width while being as short as possible for making use of that width. Everybody say hi to Safi. He's stoked. Okay, back at the kitchen table. All the batteries smushed together. Another reason why I'm laying them out like this is airflow. A little bit of air will be able to get in between each cells. No cell's going to be completely buried, but also connections. So all of my connections on one face and on the back are easily accessible. I can get to them, I can change them, I can fix them if they get damaged. I can replace cells a lot easier this way. So that's why I'm going with this layout. Basically now we're going to be wiring in series. So we have all these banks of parallels. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've numbered them all the way up to 12. Positive and negative. Basically what we're going to do now is hop over. So to get the voltage we need, right now we've got 6 cells in series per bank. Now we're going to series each, 6 cells in parallel. Now we're going to series each bank. So positive of cell 1 will go to our motors, then negative cell 2 to positive, negative cell 1 to positive cell 2, negative cell 2 to positive cell 3, etc., etc., etc. So I'm going to make the jumps over in nickel for now, just so I can keep it straight, and that will also let me solder onto these strips balance leads, so our charger can know what's what and can level out every battery, every individual cell, so they don't get off kilter and explode, because exploding is not a lot of fun. So just for example here, the positive of cell 1 will be supplying positive, for the entire battery pack, 50 volts. And then negative cell 1, positive cell 2, negative cell 2, positive cell 3, which means I'm making a bridge right here. Got my welder. Real exciting stuff. Well, it is exciting stuff for me at least. And with all these in parallel, even the series connections in parallel, my hope is to share the load across multiple contact points so as to not stress any one and make it too hot. So that's there. My next jump will be over from negative cell 3 to positive cell 4, and then negative of cell 4 to positive of cell 5. So that's the next one I'm doing on top, and then this one will be on bottom. This one will be on top, bottom, top, bottom, top, and bottom. That will be very exciting, I'm sure, so we're going to time lapse it. Okay, so all of those are welded up. Now we're going to test them. starting up here at 1, I know it'll be just out of camera, but I'll let you watch my meter here with me. And this will increase in roughly 3.4-ish volts as we measure. So as we jump from cell to cell, it'll go up. So this is just cell 1 all on its own. Oops, sorry, it's kind of hard to see there. It's just cell 1, 3.5, which is fine. Here's just cell 2, positive and negative, 3.5. Just cell 3, 3.5, etc., etc., etc. So individual cells are all in parallel, but when you go from the positive side of cell 1 to the negative side of cell 2, oh, now we're at 7.09, because it's 3.5 plus 3.5. If we go over to the negative side of cell 3, now we should have somewhere in the 11 to 12 range. Oh, well, 10. Probably running high on internal resistance. No. 3.5 plus 3.5 plus 3.5. Yeah, 10.5. My math just sucks. So that's at cell 3. Then cell 4, 14. Cell 5, 17. Cell 6, 21. Cell 7, 24. Cell 8, 28. Cell 9, 31. Cell 10, 35. 11 is 38, basically 39. And cell 12, 42 volts. So this is basically empty battery. Anyways, the reason I show you that is because the lead that I'm about to put on, the balance lead, is basically going to let the charger check the voltages that I just checked while it's charging. And depending on how the charger operates, either slightly drain the cells that are too charged or pump a little more juice into cells that aren't charged enough. So we've got to get all of these to individual cells. So the first one will go positive cell 1. The second one will go in between positive and negative of cells 1 and 2 respectively. So that will be able to tell it cell 1's voltage. The next one will go between 2 and 3, and combining cell 1 and 2, that will tell it cell's 2 voltage, etc., etc., etc. Also, to do this, we're going to be soldering, so I'm going to put my welder away. Anyways, so cell 1 over here. I mean, it's hefty, but I wouldn't say it's worse than gas. Certainly the whole thing is going to be lighter. Step 1, figuring out which side is positive, because it does matter. Be right back. Alright, so the charger I've got picked out for the job, the iCharger X12. This actually doesn't have a power supply, which is why it's so small. I had to pick up a 24 volt 70 amp power supply, but this will charge this battery in under an hour, which is pretty impressive. Anyways, on the side here we've got the balance port. So this big guy plugs in right like that, and it's saying all the way over here this guy is positive. Now they numbered their cells backwards to what I numbered mine, but whatever. So basically I'm going to give myself 5 or 6 inches. Does two things there. That will give me some room to work with the charger, but also give me some slack to connect the other cells without adding too many extensions. I do have enough wire to add extensions, but it's not something I necessarily want to do if I can help it. Solder time, using a Hako. Love the brand, FX888D. It's actually 2 parts. There's a base station that sends power to the iron. In the time that I've been talking to you here, it's already hot after I flip the switch. So there's that. Miniatronic solder. works best for me. So we're going to start positive cell 1. Just give it a little dot right there in the middle. Tin of wire. Make sure that did actually attach to the nickel. It did. And just attach this guy right here. Kind of press and hold for a second, make sure they both heat up enough to really melt the solder, not just heat it up and make it look pretty. So there's the first. Hop it over here to number 2. I'm going to go down the length of the battery, up and over, and I already need an extension. I don't know if you guys can see this. So if I have the plug sitting here, try to go up and over. Just barely makes it right to there. I guess I don't need an extension, it'll make it to that spot. The real trick to solder I found is heating up the metal and melting the solder into the metal, not dripping hot solder onto whatever you're trying to solder. So you tin both things and push them together. The wire ends, if I don't cut them off, are pre-tinned. So that one was already soldered on the end. And then the first 4 cells for the balance plug. It's going to get tedious and much messier as I go, so I'm going to time lapse the rest of it. Alright, now that we are done with that, we are going to double check everything. This stuff is kind of explosive, so I don't want to take any chances here. Again, just lining it up with the charger here. Cell 1 is on your right. That's positive, which it is. Just going to go through. This is rubber, it's not going to explode, short out anything. Just going to go through all these pins and make sure that voltages are coming through these wires the same as we measured them on the battery, and that is harder to do than said. Harder said. Right, 3.5. Oh, sorry. Starting from the wrong side, that's why I got a negative voltage. Yeah, 3.5, 7, 10.6, 14, 17 and some change, 21, 24, 28, 30, basically 39, 32, 35 and a half, 39, and 42 and a half. So that's all wired correctly. So basically, as you go through here, we got 1 cell, 2 cell, 3 cell, 4 cell, 5 cell, 6 cell, 7 cell, 8 cell, 9 cell, 10 cell, 11 cell, 12 cell. Basically, the charger knows, you know, just by doing the math and subtracting all of the cells. Like if we want to know voltage of cell 8, it would take the overall voltage of 1 through 8 and then subtract what it knows 1 through 7 to be. And that would give it voltage of cell 8, and it would know what to do from there. Some extra power in there, or drain from the others, however that specific charger works. But that's that. Now we're going to do the buses. These are going to actually carry the grunt of power, and it's going to be using this. I work my other day job installing car stuff, car accessories, so stereos, amplifiers, alarms, remote starts, that kind of thing. This is 10 gauge OFC, it's oxygen-free copper, by an audio company called Rockford Fosgate, one of the best in the business, I think. So this is pure straight up copper. What I'm going to do, I'm going to strip all of it, basically, just get a copper bar and solder it on there, probably with one across to connect all of them. This will carry more than enough for the short runs I'm doing, so I will not be covering everything in this stuff, but I will be tinning, and certainly have enough solder for it. But what's important, especially on the negative terminals, because they're not raised up, is to not get too hot. Basically, once the solder starts melting, move quickly, because if it heats up the battery, you're gonna have a bad time. Let's try that out. All right, this is actually going to be a little counterintuitive. I want the heat on my soldering iron pretty high. And you might be thinking, well, if you don't want to blow up the batteries, why do you want high heat? That's so I can get the stuff melted onto the nickel strip quickly and move on. If I have to loiter there for a long time, the heat has a bigger chance of spreading. And I realize now that the balance leads that I soldered on are probably going to come off while I do this. So that was a little counterproductive. Oh well. That will carry current. Yeah, so that again times a lot, and we'll time lapse it because that takes a long time. But the surrounding nickel is not too hot, so I'm pretty confident that it's not dumping heat into the cells. Right, so I realized that there wasn't really much point in tinning the whole entire stretch, so I've basically just tinned the ends where they actually connect. That is where I'm going to attach my main power. Yeah, this whole stretch is unnecessary, just boop, boop, boop. And then same thing, I really don't need to, with the connections already made at the battery terminal, also making the same connections along the strip of nickel between the battery terminals makes no sense, because the 10 gauge will carry more current than the nickel between them could ever hope to. So redundant, not doing that again. But yeah, let's keep trucking. So like on the other side here, well, I don't have to do it in order. I'll stay on this side. On what I consider the front. This whole stretch is going to be one shot, just the whole thing, and just one, combining them probably right here to share the parallel loads between the cells, balance them out quicker. So we'll keep doing that. Okay, well, here we are partially covered in Kapton tape because it was getting kind of hard to manage, but I did this basically one snake up the side and then down the other side. So where they cross, they're also soldered together, and so it's connected. They cross over. That keeps the balance, you know, within paralleled cells for both sides, and continues on. Fewer soldering points, and that took a long time. So I tried just now welding again. I turned it up to about 150, and it just made really cool sparks and left a little spot right there. So welding's not the way. Definitely still gonna have to solder these. I've got 1, 2, 3, just like that. Then 1 on the bottom, 2, 3 of this 3x4 size to figure out. So we're gonna keep doing it, and we're not gonna have the camera running because this video is probably ridiculously long already.
Alright, just to add some commentary to this section of the video, this was recorded pretty late and I didn't want to wake anybody up while I talked over it. I am soldering the last of the main wires for busing the power off of the last bank, the last connection, and realized that if I soldered only half of the wire, it went a lot faster and used about 4 times less solder. So I'm inserting my iron into the middle of the wire, melting the bottom of it, you know, coating it and tinning it with solder, attaching it to the top of the cell, and then twisting the wire over so that all the other strands touch the rest of it, make contact, and still conduct. This saved me a lot of time, and if you're following along at home, that's what I recommend doing, because tinning through the entire wire eats up a lot of solder, and this probably took me a good 4 hours total. I think it could have gotten it under 2 hours if I used this only solder the bottom half strategy. Anyways, back to the show.
Battery salesman slaps roof of battery. This bad boy can fit so much paramotoring in it. Ta-da! Other than main power leads, battery's done at 2 a.m. last night, which is why I left these squares off. I just trim off the Kapton tape, run it. I don't know if you caught on in that video, but I was actually running Kapton tape under the balance wire and then the balance wire on top of it and then another layer. So the Kapton tape was sandwiching the balancing wires so that if they get hot, the balancing wires don't short off against whatever cell they happen to be traveling over. It's pretty important. That's why we're using Kapton tape, because when it gets hot, it doesn't care. And then this outside here, it's, I don't know, it's like sticky Post-it notes if they were cardstock and on a roll. It's just really heavy adhesive backed paper. Usually you see them wrapped in circular, you know, cell bundles, but I did it this way. Whatever, it's protecting it. We'll make some kind of strap arrangement to actually hold it to the paramotor. But that's that. I also wanted to show you the charger I got for it here. You've already seen the charger, of course. It's this X12, but that was before seeing the power supply. Now, if you go this route, basically the company I bought this from, Buddy RC, cell's power supply that will run this charger, and it's a 24-volt power supply, so it's two 12-volt server power supplies seriesed together. That does mean that they need to be powered on instantaneously with each other, or one of them will fry the other. So that's why we have a circuit breaker with a switch on it here. Guys, we're just going to plug this guy in, make sure that's input, because the output's also XT60, confusingly enough. Hit the switch, and we're off. Lovely. Okay, so 24.6 volts. Those will get a little loud because they're really made to work in servers and they don't care how loud servers are. Plug this guy in here. And look at that. All those cell voltages. I don't know if you can see that. So right now this charger is recognizing and reporting the voltage of every cell in that battery. And you'll see they're off by 0.03 at the most. The lowest I see is 3.546. The highest is 3.549. That's fantastic balance, honestly. I'm not sure that I can charge it without main power plugged in. Let me see. I don't think it'll let me. Yeah, it's not letting me because I have to have it plugged in here. See 0 volts, 0 amps because it doesn't see anything. But the balance does. So we see cells 1, 2, 3, 4, 8, all the way down to 12. All 12 cells showing up. Variance of 3 millivolts, which is fantastic for a newly minted battery pack, and a total voltage of 42, which is basically empty. Well, it's not actually basically empty. Lithium ion, as I understand it, can be drained lower than lithium polymer, down to about 3.3 instead of 3.7. So really this is like 20-30%, which is fine. That's storage charge. But fully charged, it would be a lot higher than that. Anyways, I just wanted to show you this charger setup I have. The power supplies and the charger together were, I want to say, somewhere in the $350 range. I'll change that number on the screen if it needs to be changed, but that's actually really competitive for a 12S charger of this caliber that can charge 30 amps. So this battery can be charged in an hour. Pretty good. Turn that guy off. The fans keep running. Not sure why. They keep on trucking. Plug here. But yeah, there it is. 25 amp hour, 50 volt, fully charged, 1.1 kilowatt hour lithium battery for an electric paramotor. If you liked the video, hit the like. If you dislike it, tell me so in the comments. I've got thick skin. Subscribe if this kind of stuff's interesting, I guess. There's a lot of people to subscribe to, but it doesn't cost any money yet, so feel free to drop one down there. It doesn't hurt. And yeah, we'll see you next time when I've got something else to show you. You know, my dad built a hot air balloon from scratch. Like, all of it. He sewed the envelope. He wove the basket. He plumbed the fuel lines. Built a hot air balloon. And I'll always forget, as a kid, he told me, you know, I really feel like I was getting good at it just as I was finishing up. And I don't think I've ever related to something quite so strongly in my life before.